we will look at different levels of simplifications of the differential energy balance equation to forms which are usually used. So, let us start with the equation which I have seen in the previous slide. Now, let us say we have a ideal gas. Let us see how the above equation gets simplified. For an ideal gas, we know rho is equal to P m by R T. Let us take logarithm on both the sides, and if you now take dou ln rho by dou ln T at constant pressure, this term becomes 0 and you are left with minus 1. So, what is that? We have done taken the ideal gas, took logarithm on both sides and found out what is dou ln rho by dou ln T. Why is it dou? Because pressure is kept constant. So, that term goes to 0. So, you have got dou ln rho by dou ln T at constant pressure is equal to minus 1. So, we can just substitute that here, it becomes still simpler. So, this is the differential energy balance equation for an ideal gas. Now, let us say we have a fluid flowing at constant pressure. What happens? This term vanishes. When I say constant pressure, pressure is not a function of time and space. Remember, it is dP by dt. It has variation of pressure with time and spatial variation also. So, pressure is just a constant. It is not varying both with time and spatial location, and because pressure is constant, this term drops out. Let us go back to this equation. In this equation, if you consider density as constant, for example, let us say water is flowing, the effect of temperature on density of water is not significant. So, this term will not be significant, or if it is independent, then it is 0. So, once again that term drops out. In this case, because pressure is constant, in this equation because density is constant, both result in the same equation. Now, let us simplify further. This is the equation which I have seen in the previous slide. At this stage, we have K inside the spatial derivative. So, thermal conductivity can change with spatial location. If you assume thermal conductivity to be a constant, why should K change with spatial location? Thermal conductivity, as you have seen, is a function of temperature. So, if you have a solid object with different temperatures, then K can vary with spatial location also, because it depends on temperature. If you assume K to be constant, then you can take this out of the spatial derivative, and that becomes a second order derivative, and similarly y direction, z direction. So, you get dou square T by dou x squared, dou square T by dou y squared, and then dou square T by dou z squared. Left hand side, I have expressed the substantial derivative in terms of the local component and the convective component. Right hand side, I have expressed in terms of the Laplacian of temperature. So, this is the vector representation of this equation. Now, let us say I have a solid and then a stationary solid. Now, what happens for a stationary solid? The substantial derivative of temperature, which has two components, only the first component will remain, the second component which represents convection will become 0. So, capital dt by dt will become dou t by dou t, and that is what is shown here. So, in this equation left hand side becomes rho Cp dou t by dou t, right hand side remains same. Now, suppose if it is one dimensional heat conduction, left hand side is same, one dimensional heat conduction in a solid. Okay. Right hand side we need to take only the first term k dou square t by dou x squared. Further, if it is steady state, left hand side goes to 0 and we get a very nice simple equation d square t by dx squared equal to 0. Okay. If you look at this equation, should be really happy at it, the way in which we started taking all the energy terms into account and work done term, heat input term, several levels of simplification, you get a very simple nice looking equation dou square t by dou x squared equal to 0. Okay. So, this is for if you have a solid 1D, if you have a solid 1D and then transient is also there, and solid 3D transient. So, that is how we apply. Okay. So, we should that is why the in one sense the discussion energy balance is simpler than the discussion on momentum transport or fluid mechanics. One big difference is, fortunately q is a vector, the heat flux is a vector, it is a big simplification for us. Tau was a tensor, and many terms drop out in the energy balance equation. The terms which contribute are only few or one of them, okay, I would say. Okay, so, let us look at the analogy between momentum transport and heat transport in terms of the conservation equations. We have already seen these two equations and discussed the analogy. Same equations we will write again now in terms of the measurable variables. What is that I have done? This is the linear momentum balance, this is the Navier-Stokes equation. Substituted for tau the molecular momentum flux in terms of the velocity gradient using the Newton's law of viscosity. Let us write the energy equation once again in terms of measurables. What is that I have done? Express the heat flux, express the components of heat flux in terms of temperature gradient using the Fourier's law of heat conduction and written this equation. So, now the equations are analogous. We have the transient terms and convective transport terms, molecular transport terms, and then surface force due to pressure, body force, rate of work done by pressure force. And if you look at this form of the conservation equation, once again they are analogous. Left hand side they are written in terms of the substantial derivative. So, we have dVx by dt here, we have dt by dt here, and right hand side we have Laplacian of velocity here, Laplacian of temperature, of course other terms are also there. Of course, we should know that three such equations are there for the momentum, energy balance only this one equation alone. Okay, let us summarize this lecture. We have discussed the Fourier's law of heat conduction, which relates heat flux to temperature gradient. We also discussed the analogy between Fourier's law of heat conduction and Newton's law of viscosity. In 1D they are analogous, in 3D they are not analogous, and using the Fourier's law of heat conduction we express the energy balance completely in terms of temperature. We also looked at the simplifications of the differential energy balance equation, and finally the terms that were left out were the transient term, the convection term and the heat conduction term. Only those were the terms finally which remained in the differential energy balance equation.